Let's take a look at this setup for calorimetry. So over here on the left, we have some cold water. Over here on the right, I have some boiling water, or at least near boiling, recently boiling water. Over here I have a calorimeter, and then here I have a readout from this temperature probe. So let's look at the calorimeter a little more closely. If I open it up, there's a cup in there made of aluminum. And on the outside, in between this outer cup and the inner cup, is some styrofoam. So I got some styrofoam in there with the cup. And then there's a lid that goes on top. And this right here, this sort of pole thing, this copper colored pole, is the temperature probe. And what you'll see, if I hold the tip of the temperature probe, that's where it measures the temperature. So if I hold on to that, over there on the screen, you'll see the temperature going up. That's because it's measuring the temperature of the tip of the probe, and right now my fingers are on it. So it should warm up until it gets to my body temperature, or at least my finger temperature. Anyway, won't let it do that. So for calorimetry, one way that you can do this is you can approach it like you're going to try to figure out the specific heat capacity of this metal block right there. Imagine this is some unknown metal or new metal that you've created or discovered, and you want to know its specific heat capacity. Well, what we're going to do is I'm going to pour some of this cold water into the calorimeter. Now, water is a pretty well understood substance. We know the specific heat capacity of water, and I could pretty easily determine the mass of the water inside of the calorimeter. Just use a scale to determine the mass. And if I do this, if I stick my temperature probe into the water, I can determine the temperature of the water. Okay. Now I have this unknown piece of metal. So what I'm going to do is I'm going to take that unknown piece of metal and I'm going to bring it to a known temperature. And I'm going to do that by bathing it in the boiling water. So if I wait a moment, what will happen is that the unknown block of metal is going to come into thermal equilibrium with the boiling water. Well, if it comes into thermal equilibrium with boiling water, we know that under normal circumstances, boiling water is at 100 degrees Celsius. So if I leave that metal in there for a little bit, it should also go to 100 degrees Celsius. Okay, so in a moment, what I'm going to do is I'm going to take this piece of metal, which remember, we know its temperature. It's at 100 degrees Celsius. And I'm going to put it into the water. Now the water, I know the temperature of the water right now. It's 21.9 degrees Celsius. So think about what's going to happen. If I take some hot metal and I put it into the water, what do you expect the temperature of the water to do? Well, if I put hot metal into my water is probably going to heat up a little bit. And that's going to happen because this metal is going to lose heat and the water is going to gain heat. They will exchange heat. Okay. Eventually, when I put this metal into the water, they should reach thermal equilibrium. The water and the unknown metal would reach thermal equilibrium. So let's try it. Gonna lift this lid. And one thing that you need to be careful about is you don't want to take anything extra with your unknown metal sample. So I don't want to take any extra boiling water and put it into the calorimeter because I'm not trying to figure out anything about that water. Okay, so I'll try to drip it a little bit. And yeah, there's a string. That's not perfect. And yeah, it took me some time, and that's not perfect. But if you look at the temperature right there, the temperature is increasing. It's increasing because the hot metal is transferring heat to the water inside of the calorimeter. So the water inside of the calorimeter is increasing in temperature. Okay, and if we wait a little bit, that metal and the water inside of the calorimeter will reach thermal equilibrium. And how do we know if it's reached thermal equilibrium? Well, if it reaches thermal equilibrium, I would hope that the temperature stops changing. So let's see. All right, so now we can say that they're in thermal equilibrium. The temperature has not changed in a while, 24.1 degrees Celsius. It's pretty consistent. So with some maybe uncertainty, well, yes, with some uncertainty, we can say that they've reached thermal equilibrium. So we know what the initial temperature of the water was, right? We measured that. We now know what the final temperature of the water is. Okay. We knew the initial temperature of the hot metal because it was in that boiling water. And now we know the final temperature of the metal because it's reached thermal equilibrium with the water, so it's at 24.1 degrees Celsius as well. If we know the mass of the water, this water in the calorimeter, and we know the mass of the metal, and if we know the specific heat capacity of liquid water, then we have enough information to determine the specific heat capacity of the metal.